going to serve as a nice quick review of Unit 10. So what we did in Unit 10, we began by talking about pressure. And so there are 3 different units of pressure we talked about. And what we did was the following. We said, okay, 1 atmosphere equals 760 millimeters of mercury. Remember, millimeters of mercury comes from your barometer. Okay, which equals 101.3 kPa. All right, so you can do, and I'm going to expect you to do a bunch of conversions. So for example, if I give you, I don't know, 7 atmospheres, for example, and ask you to find how many millimeters of mercury that would be, what you need to do is the following. You just crisscross swoosh. Okay, you would put millimeters of mercury up top, nice and simple, and atmospheres on bottom. Now, you just use this equality that we have right up here in order to answer that question. So, the number you put in front of millimeters mercury would just be 760. Okay, and the number you put in front of atmospheres is just 1. So it's really nice and simple. You can do any sort of conversion. If I want to go from 360, let's say kPa, and I want to go to atmospheres, all I need to do, crisscross swoosh. I'm going to put atmospheres up top because those are the units I want to get into, and I'm going to put kPa on bottom. Now, for the numbers, remember, I'm just going to use that equality. I can do it in one step. That's totally allowed. 1 atmosphere in every 101.3 kPa. Nice and easy. Here's the other thing that we talked about pressure in this unit. If I'm climbing a mountain, okay, and I'm trekking up the mountain, as I get higher in the mountain, what happens to the atmospheric pressure is that it decreases because there's less air that's being forced down on me. Now, if I'm going to go below sea level, right, there's going to be more air that's being forced down on me, right, that's pushing down on me, and therefore the atmospheric pressure is going to increase. Okay, so that was another thing that we talked about. All right, for 2, the second thing that we talked about was changes of state of matter. So you can start with a solid, you can go to a liquid, okay, and then to a gas. So these are all of our states of matter. Now, what we call these, solid to a liquid, we called melting. Nice, easy review. I'm going to just say melt, but it's melting. Liquid to a gas, yeah, you could call it boiling, you can call it melting, but the general umbrella term we gave for it was vaporization, or I'm just going to write vapor, but it's vaporization. Now, if I'm going to go from a gas to a liquid, it's called condensation. And then if I'm going from a liquid to a solid, it's called freezing. Now, there were 2 other terms that we gave for when, for example, CO2 decides to skip this liquid phase. So if it skips and goes from a solid to a gas, we call that sublimation. And if it goes from a gas to a solid, it's called deposition. All right, cool. So that's the beginning part of this unit. Now, let's get into the heart of it. Okay, intra versus intermolecular forces. There are 2 different types of intramolecular forces. Forces can either be, intramolecular forces mean within that molecule, right? So there are 2 different types of intramolecular forces. There's covalent, right? Within one specific type of molecule, it can be covalent, or it can be ionic. Now, covalent, remember, occurs between a metal, a non-metal, my brain, and a non-metal. Now, an ionic is what exactly I said before. It's between a metal and a non-metal. Here's the thing. I can take covalent compounds and further break them down. Covalent compounds can either be described as polar or non-polar. Okay? Remember, polar, your forces are not balanced, while in non-polar, the forces would be balanced. So for example, if I'm showing you HI, I is much more electronegative than H, and therefore it's going to be pulling the electrons towards itself. There's not an equal sharing. Okay? While non-polar, for example, I'll give you the example of SCl4. I don't know, I made it up. Hopefully it exists. And notice Cl, 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 Cl are pulling in opposite directions, but they're pulling equally, so S wouldn't move in a tug of war. Therefore, this covalent compound is nonpolar. All right. Then, if we're not looking within a molecule, but between molecules, between two different types of molecules, we have three different types of intermolecular forces. We've got LDF, London dispersion forces. And remember, London dispersion forces happen between nonpolar compounds. Okay? We have dipole-dipole, which occur between polar compounds. And we have hydrogen bonding. Now, hydrogen bonding occurs between hydrogen, obviously, and either F, O, or N, because hydrogen bonding is fun. All right. Now, here are the patterns between these as far as strength is concerned, intermolecular strength. LDF is the weakest, dipole-dipole is the next weakest, and then hydrogen bonding is the strongest. Now, between these, so if I have two compounds that are LDF, and I'm having to compare their strength, they are not the same strength. Okay? What affects the strength, I can compare the strength between two LDF compounds. The larger it is, so the larger it is, the larger the compound, the stronger the intermolecular force. Okay? While for dipole-dipole, it's the exact opposite. For dipole-dipole, the smaller it is, the stronger the intermolecular force. All right. And then, if we're talking about F, O, or N, let me make sure I'm getting this right in my book. Guys, correct me if I'm wrong, but I believe I said it was the exact opposite. So it's N, sorry, hold on one second, I'm checking my periodic table. N is the weakest, so N would be the weakest, followed by O, followed by F. Okay, so that's how it works for, my pen's not working now. For hydrogen bonding. So within hydrogen bonding, anything with nitrogen would be the weakest, followed by O, then F would be the strongest. Okay, so LDF, within LDF, we can compare them. The larger they are, the stronger they are. Dipole-dipole, the smaller they are, the stronger they are, which creates the question, how in the world would you know? Now remember, as I move across my periodic table, here's a review for you. The size of your atom, so size, is going to decrease because your, sorry, my brain just turned off. My electronegativity, right, the attraction for electrons increases. So as they attract their electrons, right, so here are their electrons, and here's the center. As they attract them, the attraction for the electrons increases. They're going to pull them in and decrease the size of the atom. Okay? While as I move down the periodic table, the size increases, okay, and the electronegativity decreases. Okay, so they're inverses of each other. So that makes sense. For LDF and dipole-dipole, therefore you can compare size. The farther it is on the right, the smaller the size. The lower down it is, right, the larger the size. All right, the last thing that we're going to be looking at. Okay, and I'm going to really quickly shoot back to my notes and see if they're actually open because I wanted to show this to you guys. Okay, this is your phase diagram. All right, so if you notice, you've got pressure on the y-axis and temperature on the x-axis. So I'll redraw that here. Pressure and temperature, and you can redraw that. Okay, guys, on a test, yeah, I would expect you to be able to read the graph and answer questions just like you did for your Unit 10 quest. Remember, here this is at low temperature. This is going to be a solid, this is going to be a liquid, and this is going to be a gas. So what I would do is give you a specific pressure and temperature. You'd locate it, and then I give you a second pressure and temperature, and you'd see how that changed. So if it went from a solid to a liquid, you call it melting, liquid to a gas, vaporization, gas to a liquid, condensation, liquid to a solid, freezing. Solid to a gas would be sublimation, gas to a solid is deposition. So you guys can totally do that. Remember, this is called right here, my triple point. That is where all three states of matter coexist. All right, and I think that's all I really ask you to know from Unit 10. So there's a lot. You're talking about pressure, getting into that concept of pressure, even though in Unit 11, that's when we really hit it on the head. We introduce states of matter and changes of states of matter, even though in Unit 13, that's when we get into the energy that's involved. We really review intermolecular forces, which is from the first semester, but you guys still have to know it. The difference between covalent, which is nonmetal, and nonmetal, and ionic, which is metal and nonmetal, and the fact that covalent can then be broken down to polar and nonpolar. You can't describe ionic as polar or nonpolar, guys. Then intermolecular forces is a brand new concept that's brought up. You have LDF, which results from nonpolar compounds. Remember, the larger they are, the stronger their intermolecular force. Dipole-dipole results from polar compounds. The smaller they are, the stronger the force. And hydrogen bonding is between hydrogen and F, O, or N, and the pattern is that N is the weakest, O is middle, and F is the strongest. And finally, I go through phase diagrams, and I will expect you to be able to label things on this graph and identify whether, based on the pressure and temperature I give you, whether you're a solid, liquid, or a gas. So if you had issues with that, guys, you need to go back to your quest and make sure you're able to answer questions just like that. Okay, that's Unit 10 for right now. I will be giving you guys a review in class, and hopefully this will help to prep you for that.